Welcome. Today's discussion will be on Newton's laws of motion. Invite a friend by sharing so that many may be assisted from this. Here is the outlook, the first appearance of the chapter. Therefore, you can see it's like it is being summarized here. We have the first diagram, we have the second one, we have the third one, we have the fourth one. All these four diagrams, there is something they are trying to communicate in summary to what will be covered in the whole of the chapter. Therefore, we may go directly to the first Newton's law of motion or the law of inertia. Therefore, considering the first diagram, which is this, you can see we are having a coin that is placed on top of a card, and the card is placed on top of a glass. Therefore, it is pulled with high speed in the direction shown by the arrow. Therefore, there is something that we do expect to happen. What will be the observation? We expect that the coin will fall in the normal position from where it was placed up to the bottom. Therefore, when the card is pulled off, the coin falls into the glass. Case 2, we are having some books. When a book at the bottom is pulled instantly, the rest remain stuck. We have this guy with a motorcycle here. When the motorcycle hits a barrier, the rider flies off. It means that this person still continues with the motion. Therefore, the first Newton's laws of motion is said or stated as our body remains in its state of rest or uniform motion in a straight line unless acted upon by external force. This is also the law of inertia. That is what we summarize as from the three diagrams. We have two showing that we have to remain in the normal position, and the other one when a body is still in motion and it comes to a sudden stop. One part will continue as the rest remains. Definition of inertia refers to the tendency of a body to resist change in its state of motion. Therefore, a body in motion will be reluctant to the rest to rest, and similarly, a body at rest will be reluctant to motion. We can have several occasions. For example, uh, when a person is in a car and the car wants to move, then this person tends to move, the head tends to move backwards to resist the forward motion. And if the car comes to a stop, sudden stop, then the person will move forward to resist the sudden stop. Then now we can continue. We have momentum. Momentum is defined as the product of a mass of a body and its velocity. We know that mass is in kilograms and velocity is in meters per second. Therefore, in this case, we expect to write uh, the units in kilograms meters per second. Therefore, momentum is given by mass, which is in kilograms, times velocity, which is in meters per second. Momentum is denoted by capital P, and it is given by mass times velocity, like that. Therefore, the SI unit of momentum, as you have said, you are supposed to write in words if you are asked to state. We are told that momentum is a vector quantity since it has both magnitude and direction. The direction of momentum is the same as that of the velocity of the body. Here it is the notion P. You can have some examples here. You're told that a body or a van of mass 3 metric tons is traveling at a velocity of 72 kilometers per hour. Calculate the momentum of the vehicle. Therefore, I may not necessarily repeat this, but I'll do it aside, maybe in an easier way. Therefore, the mass is 3 metric tons, and 1 ton is equivalent to 1,000 kilogram. Therefore, we expect this one to be 3,000 kilograms. We have the velocity is given as 72 kilometers per hour, and this one must be converted into meters per second. Then it is converted by 72. You multiply by 1,000 divided by 3,600. Many a times, student will say times, I don't know, 5 over 8, I don't know, 5 over 18. But it is wrong because there is a time that you'll be in a hurry and you'll get confused and miss the question. Therefore, this one will arrive at 20 meters per second. Then now you say momentum is given by mass times velocity. And in this case, it will be 3,000 times 20. And we'll arrive at 6,000. Remember to have your units, kilograms, meters per second, like that. A car is moving at that 6 kilometers per hour. What velocity will double its momentum? From the screen, this part is already worked out, but will it try something different? We see how else we can work this. Therefore, in this case, we'll say that our first velocity will be 36 kilometers per hour, and this will be equivalent to 10 meters per second. The moment you multiply by 1,000, you divide by 3,600. Then you say, let the mass be x. You can say, let the mass be x. So in the first case, if we say let the mass be x, the first momentum will be P is equals to mv. And in this case, it will be x times 10. Can put this one into brackets so that you can show that it is the x. Therefore, this one will be 10x, and then it will be in kilograms meters per second, like that. So that is the first momentum. So now, in the second case, if we say this thing is doubled, if we say now that doubling be something that is more, more feasible. So now if we say we have doubled, then our momentum, can say this was P1, our P2, second momentum will be 2 times 10x, like that. This one will be getting 20x kilograms meters per second, in that manner. Therefore, we are being asked what will be the velocity that will double the momentum. Therefore, our mass still remains to be x. Therefore, say P2 will be given by mv. So we have 20x is equals to x kilograms because the mass of the body remains, then times our velocity v that we don't know. Then our making v the subject formula will be 20x divided by x, and then here you'll get 20 meters per second, like that. So now we can move to the Newton's second law. It says that the rate of change of momentum of a body is directly proportional to the resultant external force producing the change and takes place in the direction of the force. You may allow me to use a different format in this case. And from the statement, then we'll say that the rate of change of momentum of a body is directly proportional to the resultant external force producing the change. Therefore, we can say change in momentum, change in momentum is given by mv minus mu, like that. But now we are saying that force is directly proportional to the rate of change. So I can say mv minus mu over t, like this. And since the m is a constant, we can factor out where we can say F is directly proportional to m into v minus u over t. But we know that v minus u over t is the same as acceleration. Therefore, we'll say that F is directly proportional to mass times A. So you substitute V minus U over T with A. So now, assuming that we have a unit mass and a velocity of 1 meter per second. Should be talking of acceleration. Sorry. And an acceleration of 1 meter per second squared, like that. Then we say that force is equals to K M A, because we want to remove this sign. Therefore, since all this one is represented as 1, the K is equals to 1 because of a unit mass, which is 1 kg, and this one, then finally can say that force is also given by MA. Before we move further, you are also supposed to note that Ft is equals to change in momentum, and this part is called the impulse. It is representing the part of impulse. Therefore, that is how it is going to be like. Then now we can start having some of the examples. A truck weighs 1.0 times 10 raised to power 3 newtons and is free to move. What force will give it an acceleration of 1.5 meters per second squared? We'll still solve this one. So in this case, we're given that weight is 1 times 10 raised to power 3 newtons. This is equivalent to 1000 newtons. So we know that weight is given by mg. So our m is same as weight over g. And this means that we have how was it supposed to be? I think there is an error there. Small part with an error. Let me confirm the writing of the question. This was supposed to be power 5, so that this one becomes power 5. This one becomes 100,000 newtons. So now we can continue. So this becomes 100,000 divided by 10 newtons per kg, and you're going to arrive at a mass of 10,000 kg, like that. So now we may proceed. So from the formula of force is equals to ma. Remember, we are being asked about the acceleration. What force? So we substitute and this becomes force is equals to a mass of 10,000 times an acceleration of 1.5 meters per second squared. And this becomes 15,000 newtons, like that. A trolley of mass 1.5 kg is pulled along by an elastic cord and given an acceleration of 2 meters per second squared. Find the frictional force acting on the trolley if the tension in the cord is 5 newtons. So how will we take this one? So you consider that we're having a trolley. This one now is being pulled. And the force that is being applied there is 5 newtons. And then we expect friction to act in the opposite way, frictional force, Fr. Then now we are asked, find the frictional force is the one that we need. Therefore, number one, we need to be talking of the resultant force. So the resultant force, we mean the entire force that will be contributing to the movement of this trolley. Therefore, we say that it is given by resultant force F is the same as the applied force minus the frictional force. And therefore, F will be given by applied force. The tension of the cord is 5 newtons minus frictional force. Frictional force, which we should say, for my case, I'll say it is denoted by Fr. Therefore, now, in this case, since we have got this one, it will be easy if we put some brackets here. Therefore, we know that from the formula of force is equals to ma, we substitute we substitute F with this value here. We have the mass, we have the acceleration. Okay, so 5 minus frictional force is equals to a mass of 1.5 times 2. Here we go. So this will be 5 minus Fr is equals to 3. So our Fr, if you pick this one to the other side and this one is brought here, so this one goes to the other side, it becomes positive, this one becomes negatives. Therefore, our Fr is 2 newtons, like that. We have another example. A car of mass 1,200 kilograms traveling at 45 meters per second is brought to rest in 9 seconds. Calculate the average retardation of the car and the average force applied on the brakes. So in this case, the first thing is to analyze the question. You have a car that is in stable motion and is now coming to rest. We have been given time t as 9 seconds. We have been given u as 45 meters per second. Then now you are told that it came to a stop, or else it is retarding. Therefore, we expect the final velocity to be at 0 meters per second. Therefore, from this one, we can calculate the acceleration. Acceleration is given by v minus u over t. And this will be 0 minus 45 over 9, and you'll get negative 5 meters per second. The negative is standing for, this one is to show that the body is undergoing what you call retardation, a negative acceleration, if I can say. Then now you're asked what will be the braking force. So our braking force will use the formula of F is equals to ma. The mass is 1,200 kg times. In this case, it is advisable that you show that you had negative sign somewhere. You show that you had negative sign somewhere. So in this case, you'll arrive at negative 6,000 newtons. Now that you have already shown this negative sign, even if now you write that the final formula, the final answer is 6,000, no problem. But as long as above this answer, the one that is positive, you have already indicated that there was a negative sign, meaning that the body was coming to a stop. It is okay. It is wrong to act everything positively. For example, in this case, they have ignored the negative sign because retardation carries the negative sign. The term retardation carries the negative sign. We may proceed. Now let's look at impulse in detail. Impulse is defined as a product of force acting on a body and the type in which the force acts. Should we say impulse is an impact that occurs within a very short time? It will be still okay. We have impulsive force, and it refers to the force which acts on a body for a very short time during a collision. Therefore, as we had said from the previous formula, that impulse is given by force times t and is also the same as change in momentum. You may ignore all these parts and have this one where we had said that ft is equals to change in momentum, mv minus mu. This one is standing for impulse, and this one is change in momentum. You can have an example. But, but before we go to that example, may we have something? Okay. Yes, this part now. Can ask something that we can add. So the SI unit of impulse is Newton second. So if this one, so it's like we're saying another unit for momentum can be Newton second. It's okay. Then the rate of momentum is equal to impulse. Then Ft is equals to change in momentum, which is like this. So here we are talking of from Ft is equals to change in momentum, then F will be the same as change in momentum over T. So now this force now can also be defined as the rate of change of momentum. The rate means that we have indicated time. Therefore, if a graph of force against T is drawn like this one, then we'll say that the area under the area and the graph, then this one represents impulse. It represents impulse. Therefore, if we can make it out to this example, which is here, where you are told, let me get to a clear one. The diagram or the graph shows the force on a tennis ball when served during a game. Find the mass of the racket with a velocity of 40 meters per second. So in this case, we are first asked about the mass. But how are we going to arrive at it? The first thing is we need to look at what will be the impulse. Therefore, the impulse, just a moment. So now here impulse will be equals to mv minus mu, whereas ft is equals to mv minus mu. But now, before serving, we expect the ball or the racket to be at zero velocity. Therefore, this part will ignore to award it zero. Therefore, the impulse in this case will be the area and the curve. Area and the curve. And this is a triangle. Therefore, we expect to bother it that the area will be half into the base will be from 2 to 5. So in between, we expect how many units? 5 minus 2. Then we multiply by the height. This is 1, 2, 3, 4, 5, meaning that one small stick is equivalent, or one bar is equivalent to 100 units. Therefore, this is 5, 6, 7, 8. So we expect to multiply by 800, and this will be 400 times something I might have forgotten. That's the time here is given in 10 raised to negative 3 seconds. Then you multiply now by 800. And in this case, now you arrive at 1.2. And what will be the units? Force. And we have just multiplied NS, 1.2 newtons per second. Then now, we'll say that impulse is equals to mv minus mu, but we know that this part is 0. Therefore, 1.2 is equals to a mass of the one that we are looking times a final velocity of 40. Therefore, our m is same as 1.2 divided by 40, and we'll arrive at 0. Let me confirm. 1.2 divided by 40. 0.03 kilograms, like that. Still have another example. Determine the change in momentum produced when a force of 3.5 newtons, 3.5 times 10 raised to power 3 newtons, acts on a body which is at rest for 0.02 seconds. So what velocity will be given to the body if it has a mass of 20 kilograms? So we have a force that is already produced there. We have the time t. So that one is like giving us impulse. And we have taken 0.02 seconds. Then what are we imagining? So the body was at rest, meaning that the initial velocity is at 0. Therefore, you can see that impulse will be the same as ft, and this one is the same as 3.5 times 10 raised to power 3 times a period of 0.02 seconds This one will be giving us 70 Newton seconds. But now the question is asking, determine the change in momentum. So you can say this is also the same as change in momentum. So this is the change in momentum P. What velocity will be given to the body if it has a mass of 20 kg? Number one, you know that Ft is equals to mv minus mu. And in this case, we'll say that the initial momentum was at 0. Therefore, we'll say that Ft, which is 70 Newton seconds, is equals to a mass of 20 kg times velocity v. So our v will be the same as 70 divided by 20. We arrive at 3.5 meters per second. That will be the case. We have another example. A track of mass 2000. A track of mass 2000 kg starts from rests to horizontal rails. Find the speed 3 seconds after starting if the tractive force by the engine is 1000. This one will be a bit simpler. Find the speed if the tractive force by the engine is this. How else can we solve this one? It was coming from rests. Therefore, can go by this. So, can first look at the impulse. That was force times t, arrive at 3000. So, we have said that it took just 3 seconds and it was at rest, meaning that the initial momentum will be at 0. So, the impulse is also given by the change in momentum. Therefore, 2000 v will be the final momentum is equals to 3000, and in this case we'll get the velocity as 1.5 meters per second. I think we can stop at this and we shall continue the same parts in our next lesson. May God bless you. See you probably tomorrow. Thank you. Don't forget to share. Just drop your comments and may God bless you. Thank you.